All right. So this is my last example that I was planning to do and make a video of for relative motion analysis to determine accelerations. And this is a little bit more complicated. So let me switch over and you can, I've taken this is a snapshot from, it's a previous edition of your textbook. I don't know if this example is in your textbook, but I'm sure there's some similar to it in there. Anyway, um, let me switch over to the image. Okay, so here's the situation we have. And we're going to have um, a link which rotates about a pinned point, A. So as it rotates, it's going to drag with it link. So as link AB rotates, it's going to drag it with it link BC. It's going to pull that collar. It's going to slide straight down. And the problem gives us the angular velocity. It looks like I cropped too much here. Let's see if this works. Oh, it didn't work at all. It's supposed to have a annotation tool, but it doesn't look like it wants to work. So never mind. All right, anyway, so this should be 10 radians per second. All right, so 10 radians per second. We know the length of this rod, and we know the length of this rod, and we're given information about I apologize. This is supposed to be something we solve. So we're going to solve for this angular velocity. I took the wrong photo. I took the photo of the answer, not the original problem. Sorry. Anyway, there you go. That's the answer. So now you'll know if we get to the right spot at the end. Oh, no. That was all okay, I guess. What I what we're supposed to find is the angular velocity, there you go, of link AB. That's right. That's what we're supposed to find, is the angular velocity of link AB. Okay. All right. And they tell us omega CB, and they tell us omega AB. We know, and we're given that there's an acceleration of C, this is 1 meter per second down. So we're also going to need to find alpha CB. So we're going to try to find the two angular accelerations. All right. I'm still a little afraid that I need a little bit more of a help. Anyway, we'll work through it. Okay, going back to the problem then. Right, I think the problem originally didn't give you omega CB. We need to find it. So we have the following kind of situation. We have link A to B, and then we have this sliding element here, and this is supposed to be 45 degrees. Makes it nice and squared away. What else can I say? What I know, so let's label these. This is A, B, and this is point C. We know all the right numbers here. We know omega AB. We know that, and it is equal to 10 radians per second. We know the acceleration at point C is going to be negative 1 meter per second squared y hat. It's going to move only in the y direction, so that helps us a little bit. We also know lengths of things. We know that this length is 0.2 meters. That's the magnitude of it. And because this is on a 45-degree angle, and we know that this, although it's not drawn very well, is also supposed to be 0.2 meters, which means that the magnitude of r BC, tell you what, rather than doing the magnitude, let's just work out, just write down the actual vector. So let's just erase that. We can just work out that r, of C relative to B is simply going to be, so you start here, you're going up and to the left. So it's going to be negative 0.2 x hat plus 0.2 y hat. Everything's in meters. All right. So those are the things that we are given. What we want is to find the acceleration alpha for AB and alpha for BC. Try to find the two angular accelerations. All right. How can we do that? So the plan, assuming only this information, is, well, first off, I can write down formulas for things at B. At B, well, first off, I know that for link AB, that the velocity at A has to be 0. So A is the instantaneous center of motion for this link. And furthermore, I know that point B can only move, I should also say it's supposed to be rotating clockwise. All right. So I know that B must follow a circular path here. So that means that point B undergoes just a pure rotation about point A. That's going to simplify the analysis. In particular, we know that at the instant in the image, that B is only moving in the x direction because it's at the bottom of its arc. All right, so we know lots about we know a little bit about point B, and we want to find everything else about point B. So we want to find an expression for the velocity at point B, and then we want to find an expression for the acceleration for point B. And then once we know that, we're going to want to find an expression for the acceleration at point C using a relative acceleration analysis. To do that, along the way, we're also going to have to find the angular velocity of link BC, and that's one that the book, as I'm doing this, I'm remembering, the book actually, they referenced a previous example where they had solved for that angular velocity. So we're going to go ahead and do it all here. So I'm not going to reference a previous example. Okay, very good. So to do that, probably the first thing we should do is to let's find the angular velocity for link BC. All right, so to find that, this angular velocity, let's go back to our picture here. Here's C, here's B. Oh, sorry, here's A. And I know that omega AB is 10 radians per second and is rotating in a positive direction. Well, all right, I can use the relative, I can just say then the velocity at B is going to be RAB, which was 0.2, times omega AB, and it's going to be in the x hat direction. So that's going to be 0.2 times 10 is going to be 2 meters per second x hat. So I know the velocity of point B, and then if I do so what I want to do is find the instantaneous center for link BC. So let's see, here's C, here's B. I know that B is moving this way. I know that C can only move down. So the perpendiculars, draw the lines of action. Meet up here. And I know that these are going to have distances of 0.2 meters. So this allows me to say that this allows me to say that if I view point B as part of link BC, I can say that VB equals omega BC times RB to the instantaneous center for this link, which was 0.2. So I can write this as 2 equals omega BC times 0.2 equals, so then omega BC equals 10 radians per second. All right. So that's the first thing, and the book just assumes that from a previous example, but since we're doing it all here, I just worked it out. Okay, so now we know the angular velocity of link BC. We know the velocity at point B. What we need to do next is find the acceleration at point B so that we can use it to find the acceleration at point C. Sorry, did I say that backwards? I want to use I already know the acceleration at C. I'm trying to, anyway, I'm going to need a formula for the acceleration at B. So the acceleration at B is going to be the acceleration at A. That's nice because A isn't moving, it's pinned. Plus, so B is just undergoing a pure rotation about this point. So that's going to give me alpha times R AB magnitude. And if you think about it, well, tell you what, let's go back. Let's just write it out with the vector notation. This plus alpha AB cross the vector B relative to A minus omega squared AB times R B relative to A. That's the general formula. So let's just start with that. And then let's write this out. I'm just going to say that this equals alpha AB. I don't know that number yet. Z hat and RBA, that points from A to B. That's the negative Y direction. So this is going to be this times 0.2 times Z cross negative Y hat. Z cross Y hat is negative X hat. So that's going to come out to be a positive X hat, double negative. And then over here I have a minus omega squared was 10 squared, that's 100. And then R BA, that's going to be negative 0.2 Y hat. This becomes plus, and this becomes 20 Y hat. All right, so that's my formula for the acceleration at point B, coming from using the fact that point A was pinned. Now, and I have an unknown formula, or unknown quantity here, alpha. And right now I don't have a way to solve it. So what I'm going to do is plug this into, I'm going to use this though in my formula for the acceleration of point C, and write that as the acceleration of point B plus alpha BC cross R C relative to B minus omega BC. We found that number, that's 10. I have to square it, RCB vector. So I'm just going to plug this all in and solve for things. I know that C, that was the collar that could slide up and down. That can only be in the y direction. In fact, I know that it was -1 meter per second squared in the y direction. So I can write this as 0 x hat minus 1 y hat equals the acceleration of v. I just plug in this formula. I don't have anything better than this formula. Great. And then I have to work out this cross product. And I know, so I have alpha BC cross RCB equals alpha BC Z hat cross, and this is going to be, it was 0.2 over the square root of 2. So this is going to be, it's going to be negative x hat plus y hat over the square root of 2 times 0.2. Get that right? No, I didn't. I need to work that out again. I think I did that. There we go. RCB was negative 0.2 x hat plus 0.2 y hat. That's what I wanted. Sorry. Just write that. Z hat cross negative 0.2 x hat plus 0.2 y hat. Whew. Which equals, I still haven't actually done the work. So I'm going to have z hat cross x hat. That's a positive y hat, but there's a minus on here. So I get a negative y hat piece. And then I get z hat cross y hat is negative x hat. So both are negative when we're all done. So this is going to be 0.2 alpha b c times negative x hat minus y hat when you work that out. Z hat cross X hat is positive Y hat, but it comes with a minus sign. And Z hat cross Y hat is negative X hat. All right. Very good. So that goes over here. So then that was just an aside. So that becomes plus 0.2 alpha BC times negative X hat minus Y hat. And I have to do minus omega squared BC, but we found that to be 10, so minus 100 times the same vector. Oh, what a mess. But this is a one vector equation. There are two components, and we have two unknowns, alpha AB and alpha BC. So it's just a matter of algebra to solve this. So in particular, we could, let's see, we know the x component is 0, but that's not going to help us because the x component involves both unknowns. Let's focus on the y component. We're going to say, from the y direction, we're going to say minus 1 equals 20 minus 0.2 alpha BC minus 100 times 0.2, that's minus 20. Right? Because 0.2 times 100 is 20, and it's negative. All right. And from that, I conclude that alpha BC, well, the 20s cancel, and I get alpha BC is is going to be 5. And the minus signs cancel, so it's positive 0.5 radians per second squared. Then I can take that result and plug it into the x equation. And the x equation says that 0 equals 0.2 alpha AB minus 0.2 alpha BC plus 20. So then I can plug, so what I want to do is plug this into here and solve for alpha AB. Doing that on my calculator here, I'm going to get I'm getting an answer bigger than what I had in my notes by a factor of 10. So give me a second here. I apologize. Where did I get that wrong? Well, cheat. It came out of the book. Let's make sure. So in my notes, I have negative 9.5, but when I'm calculating it, I'm getting negative 95. Now I don't know what I did. Make sure I didn't foul that up. Oh, no, I was right. 95. Okay, sorry. I must have just had a smudge in my notes then. All right, so I get negative 95 radians per second squared. So these match what the book has. Okay, so that's a more complicated example. And the reason it's more complicated is, unlike the textbook, which just is able to quote a previous example, we had two objects here. And to do the relative motion analysis, we have to kind of work our way from one object, from one point to another, to another, to another. And at each point, you need to be able to evaluate the angular velocities and alphas. And what that means in the end is that you have to kind of work through and find the velocity expressions and the acceleration expressions for every object in your problem. And so even though the problem was about maybe about what happens, say, at a point, point C, you have to work everything out for all the points that lead up to that. And so the problems can get kind of large, and there are lots of little minus signs and lots of little ways to screw it up. So be careful, have a plan, think it through, have an intuition whether things should move clockwise or counterclockwise. Also, it's very helpful, I think, to go through and count knowns, count unknowns, think about how many equations you have. Do you have enough information to solve it? If it's a book problem or it's it's pretty standard textbook kind of problem, then it's going to have a solution. In the real world, you would have to think about it, and if you'd have to check, and if you couldn't, if you didn't have enough information, you'd have to go do an experiment or something, get more numbers. So I think counting knowns and unknowns is kind of a good idea before you dive into all the arithmetic, because I think you can kind of see it's pretty easy to lose a little factor of 2 or half or thing like that. So be clear in your thinking, which is always good advice, but especially in a problem like this. All right. See you guys.